and physics. This conversation at Shelley's home gave me the opportunity to ask about his personal experiences in physics, which will be fascinating to anyone who wants a new perspective on how fundamental physics evolved in the last century. We talked about what got him into physics as a young man in New York City, and what it was like working with the greatest physicists of the last century. We then move on to a discussion of the state of modern physics and the possibilities for the future of science. Patreon subscribers can find the full video of all of our programs as soon as they're released at patreon.com/originspodcast. I hope you enjoy the show. Shelley, it's great to be with you here. And what's really neat for me is I've known you for almost 40 years, but now I can ask you questions that I don't think I've ever asked you. Like first, why physics? What got you interested in science in the first place?
This is a question that I've thought about many times, and it's not clear that the answer I give now is the same as as what I gave 10 or 20 or 30 years ago. But when I was quite young, I had a lot of friends, but I was, on the other hand, a bit fat, and I wore glasses from the time that I was 6. So I wasn't really good at playing baseball. I was usually the last to be chosen to be on the team, and I was spending a lot of time reading science fiction in particular, and getting interested in science, partly through my brothers who were studying for medical school and dental school.
Making your mothers very happy.
Yeah, it didn't spread to me. When my time came, my father said, are you going to be a doctor or a dentist? And I said, no, I'm going to be a college professor. I'm going to teach physics. And my father said, well, if you want to do science, why don't you become a doctor and do science in your spare time?
Yeah.
And I told him it didn't work that way.
Yeah, my mother, when I first came to Harvard, my mom, I remember calling my wife at the time up and saying, he can still go to medical school. He can still go to medical school.
Right.
It took a long time. But you knew you wanted to be a college professor even in high school?
Well, that was in high school, but long before high school, in junior high, I already was very much interested in chemistry through chemistry sets.
Yeah, sure.
I was first interested in biology using my brother's microscope. He was off fighting Germans in Second World War. So I was stuck home with his microscope, and I looked at water that I collected from the Hudson River and saw all kinds of foul organisms there, and cultivated what they call protozoans, Blepharisma, Paramecia.
Yeah, I remember that.
Things like that, and had a lot of fun with biology. Of course, those were the days that when in high school they first taught biology. Fitted with me. Then it was chemistry, then it was physics. When it came to chemistry, I had something more than a chemistry set. My father built for me a little chem lab in the basement.
Oh, wow.
Where I could do all sorts of wonderful things that I should not have done. Mostly selenium. I became a selenium chemist.
Oh, really?
Yeah, I had a lot of fun with that element. It's the only element that smells like horseradish.
Oh, okay.
In all its compounds,
is there any selenium in horseradish?
No.
Oh, okay. Wow, that's great. Okay.
And then I got contacted by I published an article in a science magazine for teenagers called Chemistry Magazine, put out by the Science Talent Search people.
Oh, okay.
Science Service. Yeah. And they apparently they read it in South Dakota, and I got invited to consult on alkali disease, which is a disease of cattle.
Oh, okay.
Cattle that are attracted to plants that concentrate selenium and get some terrible disease. But I told them, no, I'm just a high school kid. I don't think I can help you much.
There's a whole bunch of things that may come to mind based on that. But first, your brother had a microscope, so he was already the one who was off fighting in Germany. He
yeah,
knew
they
he
are
wanted to be a doctor.
Yeah, the doctor to be was 14 years older than I was,
Oh,
and
okay.
the dentist to be was already practicing. He was 18 years
Oh,
older
okay.
than I.
But did they influence you? I mean, my brother was 3 years older, but I remember I was really influenced by him in a number of things. Although he didn't go into science eventually. But did did you sort of did their interest in science play off on you at all, or no?
A little bit. I remember my brother Sam explaining to me how when an airplane dropped a bomb, it had to swerve away because otherwise the bomb would explode just under the airplane
Yeah.
and things
Okay,
like
it's
that.
physics.
So
Okay.
physics.
Exactly. Now,
So,
but since you were already an accomplished chemist, selenium chemist, and biology.
no, that was my junior year.
Okay.
Then
But
we, then I took a physics course. But wait, the physics instruction. I even remember the name of the author of the physics textbook. It was a Mr. Dull. And the physics book was extraordinarily dull, and I got tired trying to memorize the 7 basic tools. I can much more easily remember the 7 dwarfs than the 7 basic tools. We learned physics by ourselves. Me and my friends, including Steven Weinberg and Gary Feinberg, both of whom
became well-known physicists,
Yes.
and as is well known, what still is remarkable to me is that for the audience is that you and Steve were in high school together, and not only both became well-known physicists, but went off in separate directions and totally independently developed the basis of what is now the standard model of physics, for which you both won the Nobel Prize at the same time. I think it's just such an amazing.
It was an amazing story.
Yeah, it really is.
And in fact, just to add some things that other people don't really know, Steve's father, when we applied to schools, I had been, and Steve were both accepted to City College, which was an obligatory application, but we were also accepted to Princeton, Cornell, and MIT.
Ah,
I was turned down to Harvard.
oh, interesting. Okay, for which you later became a professor. That's great. So was I in graduate school, by the way, and then I went to work there. But why did you?
I was turned down to their Princeton graduate school.
Okay, so we both share that. I was also turned down to Princeton graduate school, so we share that. But so why did you choose Cornell? Well, I'm jumping around, but why Cornell?
Because, well, Steve's father was kind enough to drive the two of us to these 3 schools, because we all had the same decision to make.
Oh, okay.
And when we went to Princeton, I think it was before there were girls at Princeton.
Okay.
And the Princeton guys would dress up in these filthy black costumes to dinner to try to imitate how things were at Cambridge and Oxford.
Sure.
Then we went to Cornell, which was so friendly and so wonderful. And for the first time in my life, I could see things like chickens and cows that were still alive and not on the plate.
Yeah, well, and Cornell was originally an agricultural college, wasn't it, by the way?
It was, and a major part of it was and remains. And then we went to MIT, and MIT is MIT, so we chose Cornell.
Oh, okay, that's neat. But so it was your interest, it was your friends that got you interested in, your mutual friendship that got you interested in physics. School didn't.
It wasn't school that got us into
in
physics.
spite of school.
It was in spite of school. It was the school that brought us together. It was the school that brought me together with somebody who also became a well-known physicist. Name I forget at the moment, but he taught me calculus in the lunchroom.
Oh, okay.
So
wow.
I had a little bit of calculus already.
Oh, so that's a big help.
Supplemented by, it was hard to find the right books. We would go to, there was a wonderful thing in New York in those days. It was called Fourth Avenue, because Fourth Avenue had used bookshops when there were such things as used bookshops, hundreds of them. So we would hang out there buying old physics textbooks and mathematics books.
Well, it's interesting. It's funny because my interest in science came from, in this case, a neighbor who's an engineer, and the fact that my mother made the mistake of telling me that doctors were scientists. So I got interested in science, and by the time I discovered in high school that doctors weren't always scientists, it was
quite the contrary.
Exactly, and my mother was very, very disappointed in for a long time in me and that. But what, the fact you said something that reminds me. So in those days, and for me too, it was sort of biology, chemistry, then physics, which is the exact opposite way in some ways from should be taught. As we know, both our late friend Leon Letterman,
Indeed,
it worked very hard, at least in Chicago and other places, saying that it should be. A lot of people never get nowadays. A lot of students never even get to physics, right? They start with biology. Maybe they'll do a chemistry class, and they won't even get to physics. Whereas, of course, physics is the basis of chemistry. Chemistry is the basis of biology. And the problem with learning the opposite order is you tend to learn things by rote rather than trying to figure out why things are the way they are at that basis. And so I don't know how many places have switched.
Well, it's interesting you ask, because I was at some point when my grandkids were going to school in one of them in what's it called, suburb of Boston, Wellesley.
Yeah.
I gave a talk to the class. It might have been junior high school, I'm not sure. I gave a talk to the class, it was high school, about how important it was to teach physics, then chemistry, and start with physics so that chemistry could be understood, and then learn the chemistry so that biology could be understood. And they looked at me strangely, and apparently after my talk, it turned out that they were in the process, they had just made the decision to switch to the order rational sequence, and they hadn't announced it to the yet, and they thought it was a put-up job that I was trying to convince the administration to do this, but they had already decided.
I think that, by the way, I do think I've talked to a lot of people about this. I think that's one of the people. There are many reasons people often get turned off by physics, but they get the perception that physics is hard. Even forgetting the mathematical aspect, because the high school, the rationale that I always got for teaching biology first is that it's somehow something people can appreciate because it's organisms. They can see frogs. It's something they can relate to, and it's therefore more friendly. But the impression the kids get is because it's taught last, somehow it's harder than biology, and therefore it's something you should steer away from. And I'm glad more and more places are switching. But
well, it's a difficult switch because due to the fact that American math education is so poor, it is true that physics is more mathematical than biology, and they have to be familiar with algebra, not calculus, but certainly algebra. And the things with X's and A's and B's in them, it baffles so many kids, and that's because it baffles their teachers as well.
Yeah, that's right.
So we don't have the right teaching structure yet. We don't have the people who can teach a physics course without being very gentle with the algebra.
Yeah, and it's you have to be more comfortable. I mean, that's another part of the problem, and in that, the last time I looked was a bunch of years ago, at least for middle school, well over 90 to 95% of middle school teachers who taught science didn't have a science degree.
That's right.
And they felt uncomfortable. And if they feel uncomfortable, that translates to the students. You have to kind of feel comfortable with a field in order to move beyond the curriculum enough to be able to be gentle or to go outside, what's in the book. And I think that's I've gotten in trouble because we talk about how can we change that, and I think what we have to do is ultimately recognize that in a system, in supply and demand, right now, if you have a science degree, you can generally, or certainly it's often been the case in the past, you can generally go out and get a job. And so in order to convince people with science degree to become teachers, it seems to me you have to pay them more than people who don't have science degrees.
You have to pay them more for sure.
Yeah, and that's, in the modern world, a lot of people have problems. It's not as if science is more important than English. It's just for the same reason, frankly, why generally scientists at universities get paid more than English professors at universities. Not that one's intrinsically more important. It's supply and demand and competition from outside academia, I think.
And the same is true with mathematics. And it's essential to have. I remember in high school, although I was not terribly impressed by the science teachers, although this was Bronx High School of Science,
which was
math teaching and the literature teaching were superb.
Oh, okay.
And
Literature too at the Bronx High School of Science.
absolutely.
Yeah, yeah. My best teachers were history, as it turned out. Yeah, I had, yeah, my physics class. I enjoyed physics in spite of it, but it was somewhat similar. In fact, I think that's a problem with. I was going to ask when you made the transition to college at Cornell. A lot of kids also get turned off of physics because first year physics is, inclined planes and sliding things, and it just doesn't seem. And unfortunately, also a lot of colleges, and maybe this wasn't the case at Cornell, a lot of colleges take sort of instructors and have them teach the first year course instead of the faculty, instead of the people who are going to be your mentors, the people who have some deep research interest in science, and that turns a lot of kids off too.
Yeah, well, in my case, things were different. For the calculus, I took the first term calculus. So did Steve, and we both discovered that we knew too much to take that course. So we had to skip along and go from the first semester to the third semester.
Yeah.
But the physics we had. What's the name of that physicist who put the bound on cosmic ray energies? Greisen.
Greisen. Yeah.
Greisen was a very senior guy, and he was teaching our basic physics course.
Oh, okay.
And he didn't hold our hands. It was a real tough course, even though we were mathematically sophisticated compared to many others.
Yeah.
We had to struggle with that. And
so that was what
we were thrown into serious science for the first time.
So the people who made it through there were the ones who really end up sort of wanting to.
Yeah, well, we had such a wonderful group of people, physics majors in my class. One was Tema, a young lady who became the wife of another physicist, Henry Ehrenreich, who was a professor at Harvard. Another person became the head of NASA for a number of years. What was his name?
There are lots of heads in NASA.
He recently died. A very well-known guy.
Yeah,
I forgot.
It's not James Webb, who was the head of the telescope.
No, it wasn't James Webb.
Dan Golden is. I'm trying to remember her name.
Dan Golden, we were trying to hire as the president of BU much later. That's another story.
Okay, well, we might get there. But so the bottom, I guess, in your case, it was really your peer group. I mean, I was going to ask when you had this. A lot of people, if the physics class was really difficult, you might have turned to chemistry or biology. So, but you were driven by. Well, let me ask you, instead of putting words in your mouth.
Yes.
Was it? Had you decided, based on your excitement in high school, that you wanted to be a physicist, or did that develop, or was it always encouraged by your peer group?
The peer group was also interested in science fiction.
Yeah.
And science fiction, the science of science fiction in those days was primarily physics. It was the physics of interstellar travel.
Yeah, sure.
As
I
very well know.
Physics of Star Trek was good to me. Yes.
But it was also other things. It was an introduction to philosophy, because the non-Aristotelian approach of Isaac Asimov's Foundation series referred to some philosopher, and we bought that philosopher's book.
Oh, I see.
On non-Aristotelian logic or whatever it was.
So it was a good way. It was a good entree.
But it also got us into Dianetics.
Oh,
science
gosh.
fiction.
Yeah. Oh, great. Okay, at least you escaped from.
For a while we cleared each other.
Oh, really?
We tried.
Oh.
we tried to understand each other's sperm dreams.
Yeah. Oh my God! But happily
we overcame that.
Yeah, it's good. It's good you overcame that. No, it's interesting. That's another thing, because people talk about the relationship between science fiction and science, and obviously since I wrote a book related to, at least one related to that, people ask me all the time, what's the connection? And I tend to think, it's not a connection that science, unlike many people, I don't think science fiction always predates the science or in any way understands the science, but it's this reinforcement of interest. And we actually had a joint colleague. Well, you had a joint colleague, Ben, I, for a little while at Harvard, Sidney Coleman, who was really, really huge.
Indeed.
A science fiction fan. And it's interesting that so do you think your interest in science fiction started your interest in science, or were you interested in science fiction because you were interested in science?
I
Which
think
is the
the
chicken and egg?
science fiction probably came first.
Okay.
Comic books came with the predecessor to science fiction, but
Yeah,
then
sure.
while I'm browsing in the candy store among the comic books, I found Astounding Science Fiction,
Yeah.
and that was the John W. Campbell's masterpiece book.
Yeah.
Because he also had a section in that book called Brass Tacks, which described basic science.
Oh, okay. Oh, that's great. That's interesting.
So I learned some real science from science fiction, from that journal, that magazine.
There you go. Okay, I'm gonna store that in my file when people ask me about that connection, because it's neat to know that it came directly from that. And of course, then, I mean, for me, I was interested in science fiction, but what a lot of people don't appreciate, at least in my opinion, is that it relatively quickly became clear to me that the science was more interesting than the science fiction.
Yes.
And people still seem to think it's the other way around for a lot of people, but it's science, the universe comes up with things that science fiction writers would never dream of.
The recent discoveries of the nature of the universe are so spectacular. Who would ever believe that we would know the age of the Earth to 1% and the age of the universe to better than 1%?
I would not have believed it. In fact, even I will say that when it came to the age, all the fundamental aspects of cosmology, and we'll get back to cosmology, but I remember when I was a young assistant professor at Yale, a well-known colleague of mine, an astronomer, who said to me, I had positions in both astronomy and physics, and he said the universe would conspire so that you'd never be able to measure fundamental constants to within a factor of 2. I mean, the age of the universe and the expansion rate. And because that had been history, there'd been a lot of definitive claims about age and expansion that had been wrong. And he was always convinced that observational errors would get in the way. But we'll get to that, because we'll come back to observational errors later, because there may be one that you and I were just sort of debating earlier that may be relevant to understanding whether we're still totally wrong about the nature of the universe. But let's get there. Before we get there, let's get through your history a little bit more. Why? There's two questions I want to ask. What was it easygoing, or what was your greatest challenge? I mean, was there a time when you thought of any time in your undergraduate career or even your graduate career when you thought of doing something else?
Perhaps there was when. Certainly not during college. At college, I was convinced that I was going to be a physics major and do theoretical physics, and in particular, what we like to call fundamental theoretical physics, particle physics. Of that, I had no doubt. One of the things that convinced me, incidentally, was chance contacts are so important. What is his name? Yukawa won the Nobel Prize in 1948 for his 1934 prediction of the existence of mesons. Then the mesons were seen, and he was given the prize. He came to New York to give a talk, and I noticed that he was giving a talk, and I brought my friends, and we went to the talk.
Oh, okay.
Of course, we couldn't understand a word. We were not that well informed about physics. But at the end, there was a bunch of people talking to Yukawa up front who were left, who hadn't gone home yet, and they were screaming at each other, saying, "It's a scalar, it's a scalar, no, it's a vector, it's an axial vector, it's a tensor." What the hell are they talking about, we wondered. And of course, we wouldn't know for a long, long time. But that certainly confirmed my interest in physics. Going back a few years to junior high school, 7th grade, because I just recalled this incident. I was in class. I've said this many times, but this is out of order. We went from graduate school back to 7th grade. Forgive me. I like time travel.
That's right, exactly.
So the teacher explained to me the important difference between the words rotation and revolution, that the planets rotate about their axis and revolve about the sun, and you mustn't get it wrong and say that the Earth, whatever, but the teacher then did precisely explain to us that what these things are doing, the moon, the Earth, and the sun. And I raised my hand and I said, it turns out what you're telling me is that the moon rotates about its axis in exactly the same time as as the moon revolves around the Earth, and that's because we know that because we always see the same side of the moon.
Yeah.
And she said, "That's very interesting." And I said, "Why is it true?" And she said she has no idea. That's a good question. And that was very important.
That's a great example, which I'll use because I've argued, and she was a good teacher then, because I've argued the best thing a teacher or a parent can say is, "I don't know. It's a good question. Let's see if we can figure out why."
That's right.
Because it turns learning into discovery instead of memorization.
Absolutely. Well, we didn't proceed with it at that time, but it worried me for some time.
Yeah. And I think Bill O'Reilly still doesn't understand it because he still said no one understands the tides. I remember that in a show the other day. But anyway, a year or two ago, when you talk about teachers and we talk about knowing you were going to continue to do that, and Yukawa's talk, and indeed it's interesting that going to that and hearing arguments about was important to you, because I actually, again, it's funny how in our discussion it so much resonates with me. For me, it wasn't that growing up in Canada, I didn't have access so much to well-known scientists who were from the States, although eventually I got to hear a few. But it was reading Feynman only in the sense that up to a certain point, I always thought that sort of physics was done. It had already been done in 100 years earlier. And it was only reading, I think, I don't know if it was the character of physical law, when I realized, hey, it's not all done. And I think that becomes exciting to a young person too, because when you hear people arguing, hey, maybe there's something I can do.
Yes, well, certainly things were, at the time I was going to school, there was a great deal of ferment and discovery going on throughout the 40s and 50s. The fission was discovered, after all, in 1938.
Yeah.
While I was going to school, Feynman was notorious, and he was at Cornell when I was there, though I never met him.
Oh,
but I
interesting.
had heard about him. I had heard about quantum field theory, and nobody quite understood it in those days. The only way to learn it was through some Dyson's notes. Which I actually took a course in quantum field theory as a senior when I was in college.
Wow.
But I couldn't understand a word of it. And at the end, Sam Schwaber, who was my teacher in this course,
well known,
asked me to come up and said, "You're the only undergraduate in this course, and I have a problem," he said. "I give the graduate students a letter grade, A, B, or C, but you undergraduates, and I only have you, have to have a numerical grade, so I don't really know what kind of grade to give you. What would you think an 85 would be okay?"
It's funny, but you've been anticipating my questions and what you say, but I was going to ask, you knew you want to be a theoretical physicist and a particle physicist at the time. It might have been called a nuclear physicist. I don't know what the nomenclature was.
No, it was already particle.
It was already particle physics.
Yeah.
What made you, A, decide you want to be a theoretical physicist, and B, why fundamental physics?
Well, I can't say I was a bad experimenter because I did all kinds of wonderful chemistry when I was a kid.
Didn't you also become a finalist or win the Intel Science?
I was a finalist. Intel came later. It was Westinghouse.
Westinghouse.
The Westinghouse Science Talent Search. I was one of the 40 finalists when I graduated from high school, and my project was biological. It was trying to grow tomato plants and such in the absence of sulfur, and have them replace the sulfur by selenium.
You're a big selenium back.
That's right. And I also hope to be able to produce Well, anyway, the experiments failed and the tomato plants died because I had to go away for the weekend with my folks. So.
Okay. Anyway, but so you're an okay experimentalist. I mean, what you weren't driven to theory because you didn't like to tinker or anything.
Yeah,
like
I didn't really like to tinker with telescopes or with experiments. I think I broke a few instruments in the mandatory laboratory course. It was just not something that turned me on. No, I wanted to understand. I didn't want to do.
Yeah.
I didn't want to test. I wanted to invent.
And was it particle physics simply because it was the most fundamental, or
certainly was that and relativity and quantum mechanics.
I mean, that's what drove me to the field as well. I mean, it's just the most fundamental stuff. But now you also anticipated the next question I want to ask. Describe, I mean, the state of with hindsight, I look back at the state of physics when I knew you were becoming a physicist. It was in real turmoil. I mean, for some people that would turn them off. I mean, it was just seemed to be a mess to some extent. And so, how did you relate when you became a graduate student? It was a mess.
It was the fundamental things, the things that really turned me on were a total mess. Strange particles. What nobody knew what strange Well, I couldn't even quite understand what made them strange. But they did have funny properties, and people were measuring their lifetimes, and nobody knew why they were there. We still don't know why they were there, but there were all kinds of puzzles. Then parity was violated in 1955.
Which means, somehow nature could distinguish left from right, which seems so crazy.
That was a crazy discovery. Some discoveries were not crazy. And also, I think it was in the 1950s, the antiproton was produced and observed. And that was something that was expected.
It was expected, exactly.
But all kinds of things that were not expected were happening in those days. It just went on and on. Every year or two, there was something exciting. Even in early 1950, the first pion-nucleon resonance, the beginning of the population explosion of particles.
Exactly. I mean, again, when we think about this in retrospect, and I've written about this, basically, it almost seems like a negative because every time people banged particles together, they discovered new particles.
That's right.
It looked like there was no order. It looked like it was just a morass.
There were too many particles for them all to be elementary.
Exactly. And that was not only confusing, but you might think, I mean, you could have two reactions to that, I suppose, if you're a student, saying, this is just crazy. I'm going to go to some field where this makes sense. Or I suppose if you're an ambitious young person, which I assumed you were, look, this is crazy. That means there must be something to learn. And is that what motivated you at all?
Yes, absolutely. And of course, that motivates people in many fields today, not just physics.
Exactly.
And medicine, biological science has become so much more a science than it was back then.
Yeah, for me, that's why I didn't do it. Was memorizing a frog. And now it's so much different, and also not so different than physics in many ways. I mean, the boundaries between physics and biology are kind of disappearing in many ways.
Well, I watched as my dear friend Wally Gilbert transitioned from being a theoretical physicist, hands-off theoretical physicist, to a hands-on biological science.
And he did pretty well. He won the Nobel Prize.
Well. And became a billionaire.
Yeah, well, okay, so those are both two. But not often. The only physicists I know who are billionaires are those that are failed physicists. Anyway, so the field was things were crazy, and I mean, look, the where I'm heading is kind of well known. You and Steve and others demonstrated, and I've written a book about this, and you've written beautifully about it. Took this morass and made sense of it, and you went to Harvard, and it's always interested me. I mean, I never knew Schwinger. I've written about Feynman, and I've obviously written about Schwinger, but everything I know about Schwinger seems to me to be, to some extent, the opposite of what I know about you, who I know very well. And I'm wondering how Schwinger was a very, as far as I can tell, kind of very effete, certainly formal, and none of which I associate with you. I'm wondering sort of why you chose each other.
And he was, first of all, I didn't choose him when I went to Harvard. had heard that he was there and that he was somebody important.
Well, he was
in the
brilliant.
field.
I mean, everyone
Yeah.
must have known he was brilliant.
But then when I got to Harvard, I realized that he was the only person I could sensibly work with. So what happened, it's true that he had a funny style. His lecture was precise. He had the voice of a radio announcer. It was perfect. Everything was in perfect sentences, grammatically perfect. The formulas were all clearly written on the board. The talk was so designed that he would be at the blackboard nearest the exit door. At the end of the lecture, he would end the lecture and he would simply immediately slip out the door and disappear so that his graduate students could not track him down too easily. He was standoffish, yes. But let me tell you how I became his student.
Sure.
10 or I think 12 of us showed up in his office at the same time and said we wanted to be his student. Rather, we wanted to be his students.
Yeah.
And he looked at us and said, well, let me give you all a problem. So he gave us a problem, which was to do some calculation, which we together did. And then we came back a week or two later and said we did the problem. And he explained that we had done it. And he still had the problem of what to do with this dozen students. So he gave up and he started assigning problems to one after another. One to Charlie Summerfield, who would become a Yale professor.
Yeah, he was a colleague of mine when I taught you.
That's right. Another would become, had another problem in strong interactions. Marshall Baker, he became a professor at University of Washington. The next one was Danny Kleitman, who became a famous mathematician, as well as my brother-in-law. And so it went until he got to me, which is toward the end of the group of people. And apparently he had run out of sensible problems.
Which is good.
So he said to me, Shelley, we were on a first-name basis, at least he to me.
Yeah.
And I said, yes. And he said, well, why don't you, there are certain properties that weak and electromagnetic interactions have in common. And I believe that if you make use of this Yang-Mills formalism that he hated to refer to other people.
Yeah, oh, interesting.
This was the one time that he did in my presence. Use that formalism and make a unified theory of weak and electromagnetic interactions. So that was it. He had the idea. He was the first person to imagine such a possibility.
Yeah.
And he gave it to me, and I played with it. I had convinced myself that he was right. I found other reasons that one could argue that there should be such a unified theory, but I certainly couldn't make very much progress toward finding it until they finally threw me out of Harvard and gave me a degree. But then a year later or 2 years later, when I was in Copenhagen as a postdoc, I wrote the one paper which earned my Nobel Prize, which is I found one of the pieces in the puzzle that would enable the theory to emerge.
It's the fact that he ended up, sort of directing you as a student to a problem that eventually would win the Nobel Prize is amazing, and I guess it reflects something that I hadn't appreciated about him until I was writing my last book, when I delved more into the history of particle physics and more deeply than I had ever done as just teaching it. But the notion that he understood, that he appreciated what seemed, I'm not sure, a lot of people, there's a formalism, you mentioned Yang-Mills, but this idea of this kind of theory, which we don't have to talk about here, a gauge theory, this kind of mathematics, which has become central to all of our understanding of particle physics. At the time, there weren't many people who appreciated, I think, at least my understanding, that could be so important, right? It was just two really important people had done it, or at least one, Yang but it didn't look like it would be relevant. And he said, so he had so would you say his physics intuition was good, or was it the mathematics, or what was it that drove him to that?
He had an enormous, a brilliant intuition, but coupled with this desire to do everything in a very formal fashion. That was a peculiar combination, which was very effective at some times and very bad at other times. But he was gifted in many ways. Let me give another example that happened at my thesis exam. So he had, the way he taught physics to me, he argued that electrons and muons, which are particles that are charged leptons, we call them, were known at the time, and he said, if we're going to have a quantum number that distinguishes electrons from muons, then surely it should not be the E minus and mu minus that have different lepton number, it should be the E minus and the mu plus. So that way, this quantum number charge and the new quantum number can distinguish electrons from muons. So he said it had to be that way, and it followed that there had to be two kinds of neutrinos in nature. So built into the way he taught physics, particle physics, was the fact that there are two kinds of neutrinos.
Which, of course.
Anyway, this was before
it was ever known. Of course.
Before it was acknowledged as a technical possibility by some people, but it wasn't known. Wouldn't be known until 1963.
Yeah.
This was now in the 1950s.
Sure.
So in 1958, when I went for my thesis exam to Madison, Wisconsin, because Schwinger had gone off to Madison for other reasons, got interested in condensed matter physics. Yeah. The exam took place there, and Yang, the above-mentioned Yang of Yang and Mills, was in my committee.
He was in your committee?
That's right. He and Paul Martin and Julian Schwinger and some nuclear
that's
physicists.
pretty intimidating committee, actually.
It was a wonderful committee. So I started explaining how the electron neutrino is different from the muon neutrino, and Yang said, wait a minute. I said, yes, sir? He said, don't you understand that there's no way of distinguishing electron neutrinos from muon neutrinos? It makes no sense to say they are different from one another. It's a meaningless concept. And I began to explain. And Schwinger, seeing my distress and realizing that he was the cause of it, said, let me explain the situation to Mr. Yang. And he patiently explained how an experiment could be done, namely the experiment would be done in a couple of years, how an experiment could be done to distinguish electron neutrinos from muon neutrinos if indeed they were different from one another. And Yang nodded, and then the exam continued, and I passed the exam. That would be the end of the story, except 6 months later, Li and Yang published a paper explaining how electron neutrinos and muon neutrinos could be different from one another. They simply stole the idea from Julian.
Holy mackerel.
He was subject to many such acts of thievery. Years later, by the way, I went to, only 10 years ago, I met Yang in China and was speaking with him, and I described the incident to him. And I asked him if perhaps I had remembered this correctly or not. He said, it is exactly as you said, Shelley.
Oh, interesting. Shelley, perhaps we should step back here when we talk about your working with Schwinger to give a sense of who Schwinger was and what the man was. I remember, of course, when I was a graduate student, one always wanted to work with the sort of most famous scientist you could work with, and most accomplished, and Julian Schwinger, I guess, in retrospect, of course, he's seen as a towering figure, but even in the 1950s, he was already recognized as a towering figure for what he'd done. Maybe you could talk about that for a little bit.
About Julian Schwinger, well, let me backtrack a little bit to go back all the way to the 1920s when quantum mechanics was created.
Okay.
And one of the things that the originators of quantum mechanics were very unhappy about was that quantum mechanics was not compatible with the special theory of relativity. And that was a terrible bugaboo for a long time. Attempts were made to create a theory of the electron that is consistent with relativity, and one person made such a theory, but it was inconsistent with the electron's spin. Another person made a theory that was consistent with the electron's spin, but not consistent with relativity, until finally a then young man called Paul Dirac created the theory of an equation that correctly describes the electron and is relativistic and also includes a description of spin. And that was the beginning of the marriage that would take place between quantum mechanics and relativity.
Let me just jump in for 1 second and say that that equation also predicted something that he didn't believe, and that's why he thought the equation was wrong. And later on, he said the equation was smarter than he was. But
yes, it's amazing to look over those old papers, because he originally noticed that the equation had too many solutions, and he thought that it was a unified theory. He thought that the negative charge solutions would be electrons and the positive charge solutions would be protons.
Yes.
And he realized that this made no sense, that the two things had to have the same mass. And finally he realized that he was in fact predicting the positron just shortly before the positron was quite independently and serendipitously discovered.
Yeah, I mean, it was a
positively charged electron.
And that was, I mean, I think that in retrospect, it was the reason he was so timid about it is that was the first time in the history of physics that a theoretical work had predicted the existence of a new fundamental particle in nature. And one should say, by the way, that the proton is 2,000 times more massive than the electron, so it's hard to imagine them being different.
Well, the neutron might have been predicted by Rutherford.
Maybe a little bit, but from a fundamental theory where it sort of had to be there. Anyway, I guess it's kind of amazing because the people who went out and discovered the positron weren't motivated by...
They were not looking for positrons.
It was just happened to be within 2 years of the theory that they discovered. It was kind of totally serendipity.
It was absolutely serendipitous. There have been so many such serendipitous discoveries. That's been a theme of discovery. In all of the sciences, not just physics. But then Schwinger, the marriage was not yet created because it was... The theory described how photons, how particles of light could be created and destroyed, but it didn't describe how electrons and positrons could be created and destroyed, how a photon could create an electron and positron pair, or how an electron and positron could annihilate one another to become photons. This was not part of the theory. To get that kind of theory, that would emerge as something called quantum field theory. And it emerged through the work of many people, but particularly three of them, which was Schwinger on the one hand, Feynman independently on the other hand, and in Japan, meanwhile, just after the Second World War, Tominaga in Japan. And these three were eventually recognized as the creators of quantum electrodynamics. And there was a fourth person who played an integral role as well, and that was a man named Dyson, who some argue should have shared in the Nobel Prize, but the Nobel Prize is famous for being able to only honor three people at a time. In any case, that enhanced the fame of Schwinger and Feynman, of course, and certainly Tominaga. But Schwinger had before been working on radar during the solved some radar-related problems, electromagnetic problems, classical electromagnetic theory problems that nobody else could approach. And he had been, as a calculator, he was amazing.
He was phenomenal as a calculator.
Phenomenal.
And
Yes.
I think he liked being, I think there's a famous statement about it, about his distaste of Feynman's work because everyone could understand Feynman. And he said, now this goes to the masses or something.
That's right, because Feynman had his Feynman diagrams, which Schwinger would not accept such diagrams.
Because anyone could calculate then instead of just him. Actually, do you know why? I don't know if you know why. I was always amazed in the history. Feynman and at least many of the community went to Los Alamos working on the bomb. Schwinger worked on radar and stayed in Harvard, in Boston, right?
In Boston, yes.
But I guess because it was a war effort, it was a reasonable place for him to stay, or did he choose not to go to Los Alamos, do you know? Or
I don't know if I think he felt that he was doing something useful and quite happy to be doing it there. There was no reason to get involved in anything else. And after all, you can well argue that radar played, and as well as new developments in bomb technology in fuses
Yeah.
played a more important role than
In any
nuclear
war.
weapons.
Yeah. Okay. No, I just wondered if you knew that. I never did. Okay, so that's good to know about
So
now
that
people
clears
can
up
understand
that issue.
Yeah, and so there was a good reason to wanna work with Schwinger when you went to Harvard, in spite of the fact. Also, I guess, as you say, he was perhaps the only person. Was he the only person at the Harvard at the time, sort of thinking about particle physics? Is that
Well, no, there were experimenters.
But theorists.
But among theorists, there was Roy Glauber, who had just gotten his degree, and he was certainly doing things related to neutrons and such, but more in the way of nuclear physics than particle physics.
Okay.
And there was Paul Martin, and they were doing problems in in studying the nature of positronium, which is a combination of an electron and a positron forming their own little atom. That was a big issue going on at those times. But they were not really taking students. Schwinger was taking students.
By the
dozen at a time.
By the students by the dozen.
By the dozen.
As someone, I'm sure you're the same. As someone who's had students, I've always had. There's once or twice in my life I've had more than one student at a time, and I found that very difficult.
Yeah, I had two. Two was difficult.
Yeah. 12, I can't imagine.
One of them was the Chinese young man named Andy Yao, who got his PhD with me. I took him to France in 1 year, and we were working together with Iliopolis, and we had a lot of fun. He met and married a girl who was into computer science, and she got him seduced into, not just sexually, but also into computer science. He went off and got a degree in computer science, a second PhD. He then won the Turing Prize, the highest level prize in computer science.
Oh, wow.
And went off to China to become an extremely famous scientist and well-recognized scientist in China. I've recently met him there, and he's among those who have renounced their American citizenship. He said he has not done this for any political reason whatever. In fact, he has citizenship on Hong Kong, so he can travel freely to the United States. But the reason he gave up his citizenship is that as a member of the Chinese Academy of Sciences, he is not required, he's ineligible to pay Chinese income taxes.
Oh.
But he would have to continue paying, 40% of his salary to
the United States.
America. So he decided that it was just not worth it.
Less noble political reasons.
It was
perhaps.
purely money.
Yeah. Okay. Well, that's from a perspective.
Well, he's a mathematician, so.
Yeah, so he knows about money.
Yes.
Or at least he knows about numbers. Speaking of so him moving to China, you mentioned that
China's throwing money at
it's
science.
throwing money at science, but you mentioned that Yang, who is really a revered scientist and certainly should be, and has gone back to China, one of the scientists who's gone back to China after many years in the United States, surprisingly was opposed to China building a new accelerator.
I guess he has come to the conclusion that building new accelerators has not really taught us very much. He's watched the Large Electron Positron Accelerator spend most of its time simply confirming the theories that seemed to be correct in the first place, and providing endless confirmations, Sisyphean confirmations of the theory. He's seen the Large Hadron Collider and Fermilab, neither of them making that many substantial discoveries of anything new. The last great discoveries of unanticipated things were decades ago.
Yeah, well, I know, as someone who's been working.
And you know that, and perhaps he realized, or he concluded, that there were no more great discoveries to be made. And why should we be spending so much money in this particular direction when there are so many other things that could be done with the money?
Let me, you just said something that maybe allows us to segue a little to the modern times, because we're not going to explain the Standard Model here.
No.
But I would say for the listeners that the unification of these two forces, the weak and electromagnetic, is anything but obvious. They behave very differently. The weak force operates on a nuclear scale, the electromagnetic force across the whole universe. If you were thinking of two things that could somehow be different manifestations of the same thing, in some ways, you couldn't imagine two things that look more different at this in a superficial way. You need someone like Schwinger and eventually you guys to be able to realize that there was something fundamental about.
Well, actually, Yukawa in the 1930s was trying to unify the strong and the weak nuclear interactions.
Yeah. For a long time, that was a red herring in many ways.
That's right.
And yeah, well, we could go into that, but we may or may not. But in fact, it's probably relevant to something I do want to get to, because I want to talk about string theory a little bit at some point. And the precursor to string theory was a theory in the 1960s that was trying to overcome the morass of misunderstanding about nature at that point. But before we get there, you talked about how Schwinger liked, what attracted to him this idea was probably mathematical as much as physical, the formalism that called the Yang-Mills formalism, beautiful mathematical formalism that he could appreciate. I have to tell you, I think I've told you this, but maybe not. You changed my own career in physics in many ways. But when I was
Positively,
I hope so. I was in graduate school. I was very mathematical. I was doing mathematical physics, and I remember. Well, we first met at a summer school in Scotland, and I think you. Well, anyway, I would talk to you after that, and you told me something that I always still remember and tell students. You said, "There's physics and there's formalism, and you have to know the difference." And many people get enamored with the formalism and don't realize it's not the same thing as physics. I thought I'd give you a chance to elaborate on that a little bit, because it was maybe you don't remember telling me that, but for me it was profoundly important, because suddenly I realized that if I was going to be doing something and it wasn't motivated by some experimental phenomena, in some ways I wasn't doing physics. And from then on, well, there have been a few times when I've dabbled in different areas, but I've always tied my own work to something that was related to something you could measure, or an experiment that may have unexpected results, etc. So that really changed my life.
I experienced many fads in physics during my years. First, there were dispersion relations, and they were not so disconnected from experiment as all that, but people became fascinated by dispersion relations as dispersion relations, and that led to more and more elaborate constructions such as Regé poles and the Mandelstam parametrization of scattering, and scattering as a discipline in and of itself.
And I may say that not only will members of the public who hear this not know the words, many physicists won't, because of course in some ways they went by the wayside of the dustbin of history in some way, while they're fundamentally true. Anyway, sorry.
But there are new dustbins have arisen. And of course that you are leading us to string theory, which is 40 years old as well.
Yeah, it's amazing.
It's amazing, and to things like supersymmetry, which are 40 years old or so.
So, okay, so what, in that context, and I want to get there, again, physics and formalism, how do you find it, how do you distinguish between those two things, physics and formalism?
Well, one thing that disturbs me, it's not so much a question of formalism, it's a question of one's approach to physics. And some people, like Geoffrey Chew, who was the leader of a program that has not gone anywhere.
In the 1960s, right?
In the 1960s, he was preoccupied with the concept of a program, that one must have a generalized program that would deal with all of basic fundamental physics. And so it was with Einstein when he tried to spend all these years trying to unify electricity and electromagnetism and gravity, which he regarded as the only exciting fundamental things in physics, falsely. And that, well, let's see, I'm not quite sure where I was headed.
We were with Geoffrey Chew having a big program.
Oh, it's the programmatic nature, and it spread to Schwinger, who also developed the programmatic attitude toward physics, toward his child, quantum field theory, which he and Feynman and Tomanegas shared the Nobel Prize for, but he had his way of doing things. basically the difference being that Feynman used the integral calculus and Schwinger used the differential calculus to formulate the theory.
Yeah.
And then he was led to formulating and reformulating again quantum field theory. He had his first series of papers, which are called quantum electrodynamics, his second series of papers, which were called the theory of quantized fields, and then his discovery of source theory, which was his way of doing quantum field theory, which he could practice, but nobody else could succeed in practicing, which led him astray. It led him to California with the fruits and the nuts.
Yeah.
Anyway, that was so. I never had a general approach, and I would just. My attitude was to look for the low-hanging fruit, look for puzzles that I could answer. One very quickly in my career was the psi hyperon had been discovered, and the question is, what was its parity? Could we design an experiment to measure its space-time property called parity? And Barchet and I, long ago, wrote a paper, even before my Nobel-winning paper, which suggested a plausible experiment. And so it went with little things here and there, how there could be mixing between particles apparently different from one another, that sort of stuff.
Well, and solving interesting puzzles, but they were all, but is it true? I mean, as far as I know, when I think of the work that I know of your work, which is pretty extensive, were they all motivated by puzzles in experiments? Or was it anything purely let me give you an example. Of course, one of the other than the work unifying weak electromagnetic interactions, you and James Dworkin, proposed an extra quark, which turned out to be there, and then something that really did affect, and maybe for better or worse, the future of physics, leading to supersymmetry and string theory, is the idea of what's called grand unification. The idea that maybe not just two of the forces in nature might be unified, but three of them, and you created the paradigm theory for that.
Right.
Was of all the ones, the idea that there may be a unification of the forces, the quark one I can kind of understand being motivated by puzzles and experiment, but was grand unification motivated by experiment or just something that you thought was neat?
In both cases, it's a question of beauty. And let me, it's a much described concept of beauty in physics.
Yes, and I want to get there, so this is good.
Is it good to be led by a desire for beauty, or is it dangerous?
Yeah.
And it can be argued both ways. Let me come back to the fourth quark. So I was on sabbatical in Copenhagen with Bjorkane, James Bjorkane, and we noticed that if you would have a fourth quark, then there would be 4 different kinds of quarks and 4 different kinds of leptons. There would
leptons are being like, well, you can say what they are.
That's right, the electrons and such, and neutrinos. There would be the electron and its neutrino, and the muon and its neutrino, both forming pairs with natural doublets.
Yeah.
And in quark-wise, there was the up quark and the down quark, and then there was the strange quark all alone. If you put in a term quark, there would be 2 doublets of quarks, just like there are 2 doublets of leptons, and that would make things algebraically more elegant and neat. And it was really, that was the real motivation for us introducing the fourth quark.
Interesting. So you're guilty of searching for beauty yourself.
I'm certainly guilty for searching for beauty myself. And then later, what the amazing part of this story to me is we did this in 1964, and nothing much came of it for another 6 years until I got together with Iliopoulos and Mayani at Harvard, and we used that fourth quark idea to do something very neat and create the it's described as the one great success of the search for naturalness
Yeah.
in quantum field theory.
Yes, this wonderful mechanism called the GEM mechanism, where the fourth quark and allowed you to solve a problem we won't go into.
That's right.
Which is, by the way, near and dear to my heart, because I was doing my PhD exam, oral exam, which was a general exam, a week after you won the Nobel Prize. And there were parties, or 3 days after you won the Nobel Prize, I remember that, and there were parties, and I was doing very mathematical physics, I mean really mathematical physics, and the first question in my oral exam was describe the GEM mechanism, and I looked like a deer in the headlights, and I failed that exam. So I very quickly learned about the GEM mechanism after that. So that's the importance of that is ingrained in my mind ever since then. But it was important because, in fact, it was a good reason in retrospect, that because I really wasn't keeping in touch with what was driving the physics. I was doing something called fiber bundles and gauge theories.
That's
and when I realized that I wasn't in touch with something as significant as that was a real wake-up call for me. So it was probably useful. But anyway.
There are still mathematicians out there, mathematical physicists who tell me that I simply don't understand quantum field theory if I don't express it in terms of fiber bundles.
Yeah, exactly.
I mean, they're still at it.
Yeah, it did pretty well as far as I'm concerned. But grand unification, well, it's a grand name, but it was also
not our name, and not a name that I know.
You won't take you approve. It sounds like a church, but it also basically is a beautiful. It is really it's motivated in retrospect by a number of physical ideas as well. But initially, it was a mathematical problem.
No, it was motivated purely from the search for simplicity and beauty.
Yeah.
And what by that time, physicists had learned a little bit about Lie groups, and we knew the difference between simple groups and non-simple groups. And the group responsible for the standard model, which is often called SU3 cross SU2 cross U1, is evidently tripartite. It's not a simple group that has three parts. And there were such things as simple groups, and there were what Howard Georgi and I did is to search for the simplest simple groups that contain the tripartite group of the standard model. And we found two. I found one, and he found another, which are the two simple examples of grand unified theories.
Which I remember when I was became the search for to see whether that idea was true became the central direction of particle physics in the mid to late 70s, and
it's still there. It's still lingering.
Well, let me ask you before I get to something else. I read once that you said about and you mentioned here that you were convinced that the weak electromagnetic interactions would be unified. You were convinced in 1958. You said that there must be a unifying thing, and that for one reason or another you continued to think about it. Are you convinced that now that equally it's a beautiful idea and it seems to smell right to me and many others, but are you convinced that grand unification exists out there or not?
I think there's a chance, but the current view of the universe, of the string theoretical universe, is one that makes it impossible to make such arguments, because they, as you well know, questions of that kind are now accidents of birth of our particular universe, and there's no way we can tell whether what the future will bring.
Yeah, it doesn't look like. The search for something fundamental, namely when I was growing up, and maybe one would hope it's still this way, but when I was growing up, we wanted to explain why the universe had to be the way it is. That was what I thought.
That's
physics. And now the idea is that maybe that's a bad question, that maybe it's just all a big accident. There's no real reason why anything is anything.
That's right. It all follows from Steve Weinberg's question that he asked many years ago. He said, is it that the questions we ask today about elementary particles are like the questions that people asked in the past about the radii of planetary orbits? and Kepler found some cockamamie explanation, but it was nonsense. This was not a real question.
Yeah, knowing what's fundamental is easy after the fact. It's really easy after the fact, but not when you're in the middle of confusion. Let's talk a little about string theory, because there's a quote from yours I was reading. I reread it just in anticipation of this, an old paper you wrote, a little I guess it's a paper, the paper Desperately Seeking Superstrings from 1986.
Yes, that was co-authored with
Paul Ginsparg,
yes,
who's now Cornell, who created something in
who was a string theorist at one time.
Yes, and yeah, there was a number of criticism or interesting discussions. It was actually, when I read it at the time, I remember it caused a stir because everyone thought it was so heretical, but it's actually kind of kind in many ways. But it does say, in lieu of the traditional confrontation between theory and experiment, superstring theorists pursue an inner harmony where elegance, uniqueness, and beauty define truth. And that was, and you were criticizing things because you said that the instead of the confrontation between theory and experiment, and it's rather interesting for me and you. I know that for us, for me still, I'm an old-fashioned physicist in the sense that whether something, when you have an idea, what really matters is, does nature, obey that idea? Does it explain anything? Does it explain experiments? Whereas there's a whole generation that's grown up that says, is it a beautiful or elegant idea? That's more important than whether it actually explains anything. And that's a problem, don't you agree?
I think it's very much a problem, and well, let's be careful. The superstring people are very smart.
Yeah, absolutely. And it's in many ways, it's well motivated. It's motivated by gauge theories and the kind of things that the Standard Model built up, and some puzzles in the Standard Model, after all. Like why?
No, yes, there are puzzles remaining, but the real why questions that I'd like answers to is, why are there 6 kinds of quarks? Why are there 3 families of quarks and leptons? Why is there this particular tripartite group?
Yeah.
Things like that. Why? Well, not exactly why questions, but how did it come about that there are
all why. I've said it before in my books. All why questions in science are really how questions. Don't assume there's purpose, but we want to know how the universe came to make. And you're right, in the Standard Model, which is beautiful, and by the way, I've argued is the most amazing triumph of the human intellect that I know of. The whole journey to the Standard Model that describes nature in ways that I must say, even when I was a graduate student, I never thought we'd
reach such a point.
We'd reach such a point. But that beautiful model has 17 or so.
It's not so beautiful when you look at it with the microscope. It's quite ugly, in fact.
It's like Impressionist paintings, I've always said. So from a distance, they look great. We walk up close, they look pretty bad. And so that certainly is a cause, at least for some of us, of concern, right?
But another cause for concern is that there is no experiment that contradicts the Standard Model.
And it's exactly that. I think that, certainly, again, when I look at history and when I look at even things that have happened since I've been a physicist, that it's those contradictions, it's those puzzling things that come up that drive theoretical physicists. Theoretical physicists can come up with a lot of stuff. If you lock them in a room for a long time, they come up with beautiful things that had nothing to do with the world, because the imagination in nature, in my experience, is a lot better than the imagination of human beings. It's the experiments that drive us and tell us what's the right direction.
That's true. And the tragedy of the moment is that the Large Hadron Collider, which is the most powerful accelerator working today, has not found any surprises whatever, just merely finding, merely is perhaps the wrong word, discovering the Higgs boson.
Yeah, exactly. It was a huge triumph, both intellectually and experimentally, to be able to discover this.
Absolutely.
And some people may think that that's, but what, from a physicist's point of view, what you like to be at some level is wrong. With something about the Standard Model we hope is wrong, namely disagrees with the experiment, so that we can tell us where to go beyond it.
Exactly, and that's what's missing at the moment.
Yeah.
Maybe tomorrow they'll find doubly charged leptons, or who knows.
Well, let's go to the future now. I think it's a perfect segue to that, to think about, well, the puzzles that exist now, and we can talk about some of them. And as we talked about before, some of them are in cosmology, which are interesting.
Indeed.
When I was doing my PhD, I actually started as a particle physicist, and I've been a particle physicist, but I started to think about cosmology. At the time, that was sort of new. But now, in a way, what's happened in the last 30 or 40 years is because accelerators have been limited in the new things they've been able to tell us, we look at the universe, which was a particle physics experiment after all, and the early universe had energies that we can't access with our current accelerators. Many of us have looked at the universe to try and find clues that might take us beyond the standard model. And the question is, when the Large Hadron Collider came on, great, suddenly particle physics could access something new. And we all thought, many people thought, not just the Higgs, but many people thought that would discover this thing called supersymmetry. It hasn't. Do you have any sense from your gut intuition where what the likelihood is that the Large Hadron Collider might discover something new and where it might come from? You have a pretty good track record.
Yes, but not recently. The Large Hadron Collider has not found anything unexpected, and it's unlikely that it will because its energy is compromised compared to the what we all knew was the right energy that was needed with the superconducting supercollider.
Which I should preface was a tragedy in many ways for science and for this country. There was an accelerator being built in the United States which was designed based on the physics problems, designed from scratch based on trying to solve the physics problems, and the United States decided the government of the United States decided in its wisdom that we couldn't afford to build this thing, which may have cost $10 billion, which is like as